Okay, we're going to look at the first question. This is quiz number 6. A rectangular waveguide with dimensions given as such. So if we want to look at this waveguide, basically, this is question 1. So what does a waveguide look like? Basically, it is something like this. Okay, so let's say this is our x direction and this is the y direction, right? So this is x equals 0, and this is I'm sorry, that last part is x equals 0, and this is x equals a. So similarly, this has to be y equals 0 and y equals a. Now, as it is given in the problem, if we just go back to the problem here, the z component of the B field can be written as x of x times y of y, and x and y are given here. So we need to apply the boundary conditions, which is indicated as dx over x vanishes at x equals 0. So let's do that. So here if you take dx over x, dx over dx is equal to a cosine kx x obviously I missed out kx there, so a kx cosine kx over x plus, and then b kx minus sine kx x. Okay, so now if we plug in x equals 0, what are we going to get here? So at x equals 0, we have the second term here. This term vanishes, so that means it will be just a kx cosine 0, which is 1. So a kx equals to 0, and this gives us a equals to 0. Okay, that's our first result. So we know how x f of x looks like now. It just has b component, b cosine kx x. So if we apply the same condition, the derivative of x with respect to x at x equals a, we're going to get so dx over dx at x equals a, then that will be equal to minus b kx sine kx times a, which is equal to 0. So what do we have here? If b is non-zero, right? So b is non-zero, kx is non-zero, so that means sine kx times a must be 0. And for that to happen, we need to have kx times a is equal to m pi, where m could be 0, 1, 2, etc. Okay, that's our second important result. And you can repeat the same thing for the y part, and you'll get another condition for y, and let's write that condition directly. So the same thing happens there. It should be at y equals 0 and y equals b. So what condition do we get there? Basically, we get ky times b equals to m pi, right? And again, no, not m. In this case, it's called n pi, and n is again 0, 1, 2, etc. All right, that's our second important condition. Now, we also have, as you see here, kx squared, ky squared with the minus signs, omega over c squared minus k squared equals to 0. So now if you use this condition, you can write k, the propagation constant, in terms of kx, ky, and omega over c. So that will be very useful. Let's do that. And so that would give us k equals to square root of omega over c squared, okay, minus kx squared minus ky squared. Now, this has to be real, all right? So that means within the square root, we need to have a positive number. So for that, we can get a condition for omega for any propagation vector. So for any m and n that we can pick, if I have m equals 1, n equals 0, for example, I can do that. So if I write this condition, then it would be for omega needs to be greater than, these all have pi, m pi over a kx is, or n pi over b ky. So if I plug those in, I'll get the following condition. So omega should be greater than pi c square root of m over a squared plus n over b squared. Let's write an answer. Okay. So we need n combinations here. So if I have m equals to 1, n equals to 0, omega must be greater than. Okay, so now I have pi c, and then I have square root of m equals 1. And for a, the problem gives 1 centimeter, so that's 10 to the minus 2 meter. That's squared. So that means omega must be greater than pi c. 1 over 10 to the minus 2 will bring 1 over 10 to the minus 2 outside the square root. So that means 3 times 10 to the 10. So it has to be greater than 3 pi times 10 to the 10 hertz. Okay, that's the first result. Now, I can try some other quantities. For example, I can try m equals 0, n equals 1. Well, that will give me something. Okay, omega is now greater than pi over c times, all right, let's redo that part. Okay, m equals 0, n equals 1. Okay, omega is greater than pi c square root of. Now, what do I have? I have, again, 1. However, the other direction is given as 0.4. So I have 0.4, 10 to the minus 2 squared. Now, that will lead to, okay, again, 0.4 comes out. So outside, I will have 3 pi over 0.4. Okay, so 30 over 4, that's 7.5. So omega must be greater than, say, 15 over 2 pi times 10 to the 10 hertz. Well, am I done? Is it just between those two frequencies? No, because I should also check basically m equals 2, n equals 0, or m equals 0, n equals 2. If I have any of those, well, for n equals 2 it won't work because it's going to be double this frequency. It's even going to be larger. So I need to just check m equals 2, n equals 0. So let's do that. So if I have m equals 2, n equals 0, then I'll get the double of the first frequency I found, which has to be 6 pi times 10 to the 10 hertz. Okay, then that indicates that it has to be between m equals 1, n equals 0, and m equals 2, n equals 0. So if I operated at that frequency, only a single mode can propagate. I have only, okay, so conclusion, okay, I should have 3 pi 10 to the 10 hertz smaller than my frequency omega, smaller than 6 pi 10 to the 10 hertz. Okay, that's the final result. Thank you.